All right, we come back wrapping up section 2 and hence all of chapter 10. So we're going to do the talk about comparing two means. So where you have paired data, a little different here. So research studied a random sample of identical twins who had separated and adopted at birth. In each case, one twin A, was adopted at a high-income family, the other by a low-income. Both twins were given IQ tests as adults. All right, so we kind of see what's going on there. And twin A, the high-income family, twin B. Okay, so we look at those dot plots, those distributions. As we're kind of looking at those, might want to kind of look at some things. So twins raised in high-income households had a higher mean of 109.5 as opposed to 103.667. There's similar amount of variability, 9.47 for the first, for the high income, 8.66. So pretty similar variation as we're kind of looking at that. But with so much overlap between the groups, the difference in means does not seem statistically significant. Now, the previous analysis ignores the fact that these are paired data. Now, again, that's kind of the idea, is that paired data results from recording two values of the same quantitative variable for each individual or for each pair of similar individuals. So we're matching them up is what we're doing. All right, so what we might do is find the difference between each of the paired twins. Okay, so we kind of find that difference. We're going to go A minus B, and in many of those, all but one, we see A is more. All right, and we can kind of plot that out on that difference is what we can do. Now, the mean difference, of course, would be 5.833. So if we just found the average of those differences. The standard deviation of those differences, of course, is 3.93. Now, the proper method of analysis depends on how the data are produced. Okay, remember that. Now, to analyze paired data, start by computing the difference for each pair. Then make a graph of the differences. Use the mean difference and the standard deviation of the differences. Notice the subscript diff. All right. So here we go. So now we have this. Does music help or hinder performance in math? Student researchers, Abigail, Carolyn, and Leah, designed an experiment using 30 student volunteers to find out. Each subject completed a 50-question single-digit arithmetic test with and without music playing. For each subject, the order of the music and no music treatments was randomly assigned, and the time to complete the test in seconds was recorded for each treatment. Now here's the data along with the difference in time for each subject. Okay, so you had a student, you had time with the music and time without. And you kind of look at that difference that you have there. I think I know where this is going, and I've seen many studies like this before. As kids always say, oh, listening to music helps me study. Well, we'll see. We'll see. All right, so we're going to make a dot plot about the difference. So we're going to take the listening to music minus without in time for each subject to complete the test. We're going to describe what the graph reveals and then calculate those mean differences. All right, so we're going to take music minus without music is what we're going to do here. All right, so we've got that. There's our dot plot with that. There is some evidence that music hinders performance on the math test. 17 of the 30 subjects took longer to complete the test when listening to music. I guess even more. All right, so if we do find those differences and we find the mean, it's about 2.8 seconds. Standard deviation of the difference is 7.49. Now, so the time it took these 30 students to complete the arithmetic quiz with music was 2.8 seconds longer on average than the time it took without the music. All right. Now, there are two ways that a statistical study involving a single quantitative variable can yield paired data. Researchers can record two values of the variable for each individual. So you could do like listening to music, whether listening to music helps or hinders learning. And again, the researcher can form pairs of similar individuals and record the value of the variable once for each individual. So we could do observational study where we're looking at identical twins IQ scores. So a couple different ways of kind of pairing up that data is what we're doing. Now, it is possible to carry out a match pairs experiment using method 2 if the researcher forms pairs of similar subjects and randomly assigns each treatment to exactly one member of every pair. All right, so now again, conditions for this, we've seen this many, many times. Okay, it's got to be random, 10%. Now when sampling without replacement, make sure that the sample size of our difference is of course less than 10% of the population of differences. And then of course our normal large sample, we've talked about that, is that make sure it's normal or at least our sample size is large, in other words, bigger than 30. or else you make a graph and make sure that there's no skewness, no strong skewness or outliers. Those are kind of what we have to make sure to do when doing those. Okay, so now when we're doing this now we're going to take the mean of those differences. We still have our t-score that we have there, standard deviation of the differences, and then the square root of the sample size of the differences. So we're just going to do those differences first. So let's go through another example of this now. The data from the random sample of identical twins is shown again. Okay, so we have that. So we want to construct and interpret a 95% confidence interval for the true mean differences in IQ scores among twins raised in high income versus low income households. All right, so here we go. So state it, 95% confidence interval for the mean difference where you use some difference. This is the true mean difference, high minus low income, for IQ scores in pairs of identical twins raised in separate households. Now, plan, again, we're going to check the randomness. Yeah, it's random. 12, I would assume, is less than 12% of all identical twins, yes, raised in separate households. I would agree. Looking at this, it does not show any strong skewness or outliers, so I think we're okay, even though our sample size is not bigger than 30. I think we're still okay there. All right, so let's do it. So the mean difference, if we did that, if we average up those differences, was 5.83. The standard deviation of that, of course, is 3.93. And the sample size is 12. We have 12 data. So where the degrees of freedom is going to be 11, so we find our t-value to be 2.201. So putting that in, we're able to find a confidence interval here of 3.336, 8.33. Now don't be afraid to use our friend the calculator on this as well. Okay, use the two samples, so make sure to take a look at that. All right, so here's our deal. We're going to take a look, conclude we are 95% confident that the interval from 3.336 to 8.330 captures the true mean difference from high to low income in IQ scores among pairs of identical twins raised in separate households. So there we go. We'll get some practice with those again on page 685. There's some good ones there with 37, 41, 45. Great multiple choice questions, 49 through 52. We'll get those taken care of, and then we'll begin our review with our multiple choice form assessment and our FRAPI, and get ourselves ready to go for that Chapter 10 test. So building on a lot of things that we've already talked about, but moving on. So remember those learning targets. Look through that chapter summary, and we'll get ourselves ready to go to perform well on that test. And until next time, I'm Mr. Boone.